Welcome back everyone. In this lesson we are going to learn about another method for finding out the solution of simultaneous linear algebraic equations, which is known as the matrix inversion. So I guess all of us already know how to invert a matrix, and we have done this so far in our linear algebra courses. So I guess this lesson would be very easy for you to understand. So suppose we are given a matrix which is denoted as A. So A is a square matrix. So before going into the details of matrix inversion, you have to remember that matrix inversion is possible only for a square matrix. So if the matrix is not square, you cannot invert it. So the matrix should be a square matrix. Another precondition for matrix inversion is that matrix cannot be a singular matrix. You must have a finite determinant value of that matrix. So remember, these two conditions must be filled to invert a matrix. Now let's dive into some of the properties of matrix inversion and inverse of a matrix. If A is a matrix, then the inverse matrix of this matrix is denoted as A inverse. So this is the inverse of A matrix. And if we multiply these two matrices, A multiplied by A inverse, this is a matrix multiplication. This is not the normal element-wise multiplication. So be aware of that. So whether it is A inverse times A or A times A inverse, this is the same, and the result would be an identical matrix I. So that's the definition of inverse matrix, that if we multiply a matrix with its inverse value, we will get an identical matrix. So how a matrix inversion can help you to find out the solution of a system of linear algebra. So for example, let's say we have a system which is denoted as A times X equal to B. Here A is the coefficient matrix, X is the unknown variable matrix, or we can say it's a vector of unknown variables, and B are constant matrix. So we can easily compare this equation with the general equation of system of linear equations that we have learned in our previous lessons. So here A is the coefficient matrix. So if we multiply with the inverse of A on both sides of this equation, then on the left hand side we have A inverse times A times X equal to A inverse times B. On the left hand side, the multiplication of these two terms, A inverse and A, should be an identical matrix. And if you remember, if we multiply any matrix with any identity matrix, the result would be the same of that matrix. That means I times X, it should be X. And on the right hand side, we have A inverse times B. So in this case, if we can find out the inverse of A, then multiplying that inverse matrix with the constant matrix, we can easily find out our unknown variables X. So that's the main theme of using matrix inversion to find out the solutions of a system of linear equations. So that's the main formula that we are going to use. So remember, in the last equation, the final equation, we had X equal to A inverse times B. So the formula was derived from the theory of matrix multiplication. So you have to be careful about the multiplication. It should be A inverse times B. That means the A inverse should precede the constant matrix. It should not be the otherwise. That means B should not precede the inverse matrix. So be careful of that. So let's find out the inverse of a matrix through adjoint method. So I guess you already know the method to find out the inverse of a matrix, but this is just a simple overview of that method. So let's say we have a matrix M which is denoted as this. It's a 3 by 3 square matrix. So if we find out the determinant of this matrix, the determinant turns out to be 1. So it's not a singular matrix, and also it's a square matrix. So that means we can find out the inverse of this matrix. That means the inverse exists. So we are sure of that. So what we are going to do, we first determine the transform of the original matrix. That means we transform the matrix, which that means we convert the rows to columns and columns to rows. So the resultant transformed matrix is like this. Next, we calculate the determinant of each of the 2 into 2 minors of these matrix. So what are the 2 into 2 minors? We consider each minor, which are 2 times 2 matrix, and we calculate the determinant of each of those. For example, the first minor, that means 1, 4, 6, 0. The determinant of these is minus 24. Similarly, we calculate the determinant value of all of these minors, and then we consider we construct the adjoint matrix of M, considering these minors, and then we multiply these with the symbolized matrix form and get the original adjoint matrix notation. So once we get the adjoint matrix, we divide the adjoint matrix with the determinant value, and we will get the inverse matrix, which is something like this. So this is our inverse matrix of the original one. So once we get the inverse matrix, we can easily get the unknown variables by multiplying the inverse of the matrix with the constant matrix. So let's look at an example. Let's say we have this system of equation, and there are some constant terms on the right hand side, which are 1, 4 and 5, and also these are the constant terms, and also we have some coefficients on the left hand side. So if we consider each of the coefficients and construct the matrix, we will get the coefficient matrix something like this, which is denoted as M. So we need to find out the inverse of this matrix. We already have shown the method to find out the inverse of the matrix, or you already know the methods, because it's a very simple linear algebraic approach. So once we get the inverse of the matrix, this is the inverse of the matrix, and then we multiply this inverse matrix with the constant matrix. Constant matrix is 1, 4, 5. It's a constant vector actually. So if we multiply these two matrices, this is a matrix multiplication, and after multiplying this, the resultant will be a 3 by 1 matrix. That means it's a vector of length 3. On the right hand side, we will have the unknown variables. Since x equal to the inverse of the matrix times the constant matrix. So x1 equal to 73, this should be x2, there's an error here, x2 equal to minus 60, and x3 equal to 16. So in this way, using the inverse formula of matrices, we can easily get the unknown variables. So in this lesson, we have learned about the inverse of a matrix. In MATLAB, we have a function which is called the inv function, inv, which is used to inverse a matrix. But a matrix inversion is not an efficient approach to find out the solutions of linear algebraic equations. So this is a very straightforward and easy one. We can easily use this method to find out the solutions, solution of a system that contains a limited number of equations. In the next lesson, we will learn about another very popular method for finding out the solution of a linear system, which is known as LU decomposition. And we will see that these LU decomposition can be easily used to find out the inverse of a matrix. The inversion method that we have used in this lesson, which is the adjoint method, this method is not so much efficient because we need to calculate there are lots of multiplications, there are lots of additions and multiplications, and that's why this is not good for computational applications, and that's why we are going to use LU decomposition to find out the inverse of a matrix. And we also see that LU decomposition can be easily implemented to find out the solutions of a linear system. So till then, thank you so much.